All right, so your assignment number 2 has been released. Please double check the deadline. Your programming test number 2 is going to be based on assignment 2 and 3 about graphs, okay? So just make sure you kind of struggle through the problems and then redo the assignments. Once I release the solution, you can definitely compare. Your tutorial number 7 is going to be tomorrow in person. So we're gonna meet SLH, and then we'll talk about something interesting about loop invariance. I'll give you guys some introduction today, I'm sure, and then we're gonna continue with some exercise to really walk it through. That'll be the plan. Okay. Guys, any questions in general about the course, right? You pretty much know what to work on, right? Okay. And your written test is going to come on March 19th, I believe. I'm gonna give you guys a guidance, like a PDF, just to give you about expectation, coverage, etc. next week. So you can definitely, but just start going over the materials. I think that will be the safest bet. Okay. Quick recap. Okay. So last time we spoke even more about properties comparison between breadth first search and depth first search. So this is just more like a piece of code, given that the depth first search or breadth first search is already working. How can you kind of extend it to calculate, for example, how many connected components you have in the graph, right? That's just one example, okay? And then we talk about spanning trees that you can get from doing the traversal. And this table here is very important, right? So when you study for this part of the lecture, always start with this table. I wouldn't recommend you kind of just memorize it. Think about what's really being said over there, right? I'll just give you the essence about the highlights. When you were doing depth first search, and also, well, let me say it again. When you're doing depth first search, if it is undirected, you only have to worry about discovery edge and back edge. In the case you got back edge, that means yes, there is a cycle. And similarly for directed graph as well, when you do depth first search. The thing is, when you do depth first search on directed graph, you might run into forward edge or cross edge. When you run into either kind, you cannot conclude or return right away to say there's a cycle. There might be a cycle elsewhere in the graph, but not the current part you're visiting for the forward edge or cross edge. It's a very important distinction to make. And when you do breadth first search, either on undirected or directed graph, as soon as you let me say it again. When you're doing breadth first search, if that's on the undirected graph, in that case, if you see the cross edge, yes, there's a cycle, almost like a back edge for the depth first search. But if you're going for other cases, it will be not necessarily, which means you cannot conclude right away. All right, so guys, please go over those examples we went over, right? I may not go over them in detail again, just go over them, okay? Make your own example as well, okay? And then, so that's just about adapting the DFS to answer different questions. One thing I want you to also pay attention to, you may want to do some programming exercise as well. How do you really represent a spanning tree? Let's say, for example, for this particular depth first search, we got a spanning tree that will have 1, 2, 3, and 4 discovery edges. The simplest way to really represent a spanning tree is by having maybe a hash set of edges, which is going to contain all the tree edges that will form the spanning tree. That's one way to go. Or maybe sometimes I want you to include maybe the vertices as well, right? Just keep some flexibility there, right? So that's something you want to really try to practice. Okay, you can look at other graph questions as well, which we spoke about last time too. All right, and this one here, the same questions about graph, just see how you can answer them using breadth first search. Okay, you can do that as well. All right, so that's the new topic that we kind of started. All right, we're gonna just revisit the terms very quickly, and then we're gonna do some tracing and also understand Dijkstra algorithm. So talk about a new kind of graph. It's called weighted graph. That means for the edges, we're going to annotate each edge with an integer value called the weight or the cost. So the weights, we assume that it's going to be non-negative. Cannot be negative because the Dijkstra algorithm simply is not going to work if you got negative weights. We'll see exactly how. Okay? So you got weights, things like this, and then you got the definition for the weights or length of a path. Simply sum up the weights for all the edges involved in the path. And this little d here is so important. We're going to see that when we do the algorithm. Little d here simply means what's really the shortest distance or shortest weights for two vertices if you want to connect them. For example, between, let's say, Los Angeles over here. Los Angeles and also New York. That's it. Between these two cities, there are more than one way that you can travel. You can go either this way, path number 1, or you can go maybe path number 2 in this way, and etc. It turns out this green path is the shortest one, and we say that the summation of the weights is the distance, length, or the weights of that particular path, right? The minimum. All right, we're going to use this concept here very often when we try to learn an algorithm. Okay? And in the case where if the two cities are not really connected by any edge, conceptually it's simply infinity. That's the maximum weights possible. Okay? Any questions about the terms that we're talking about on this page here? Okay? All right. All right. All right, so now let's talk about something to continue from Monday's lecture. Okay? So for those of you who arrived late, you're just right at the right time. Okay? You can see the exact algorithm. Okay? Okay, let's now go over this algorithm carefully. Okay? We divide this, first of all, this algorithm, Dijkstra algorithm for shortest path into 2 stages. Okay? Stage number 1 will be for initialization. Okay? You can think about this part here will be initialization. The first one here. This part here, let me make it a little bit smaller. Okay, bullet point number 1 will be stage number 1. That's more like initialization. By the way, so the way we're going to learn about Dijkstra algorithm, we don't see the Java code just yet. When we analyze the running time later, I'm going to show you some Java code. But for now, we're just going to focus on bullet points, like get some intuition. Okay, so this part here is for initialization. And then the second phase, bullet point number 2. We have this part here, all right, this part. This part here is going to be a double loop, like a nested loop. However, you don't really want to think right away, if that's a nested loop, it must be n squared. Don't go there just yet, all right? So that's something we'll see. It involves something a little bit more sophisticated to actually analyze, which we'll get to a little bit later, okay? So this will be the iterations. Let's go a little bit deeper about how many iterations do we need in total. First of all, basically, we have some priority queue. And then we're going to initially put all the vertices into the queue. And as soon as the priority queue becomes empty, we're going to stop the algorithm. So you can think about the outer loop is really about adding, given that we got a queue containing all the vertices to start with. And we're going to, for each iteration for the outer loop, we're going to remove one vertex from there once we have visited that or processed that, right? So for the outer loop, the number of iterations will be number of vertices. Because initially we put all the vertices into the priority queue. Remove one at a time. And we never put any vertex back once it's removed. A little bit like a depth first search, right? You don't really push a vertex back to the stack once you have popped it up. Okay? And there's an inner loop right here. We say that for every vertex, let me show here. For every vertex that's in the queue, we choose one at a time. And for any particular vertex we have chosen, we have to go for all its adjacent vertices. All right? So for example, let's say if I choose this particular vertex, let's say X. For the inner loop, how many iterations do I need maximum? I need to go reach out to all the adjacent vertices and try to process them. So it'll be up to the degree of this particular vertex, right? The degree, okay? So this one here will be inner loop. Inner loop. So the number of iterations here, I'm going to say up to. Okay? Up to in the sense, well, the number of iterations will be exactly equal to the degree of u. However, the actual cost for us to really process for each iteration may not be the same. Sometimes we may just be able to skip right away, right? That's something I'll get to a little bit later, okay? And of course, as soon as we see the degree over here, so we know that it will be expensive if the graph is rather complete, meaning that we got basically this vertex may be connected to every other vertex in the worst case, right? So we got to be careful, right? When the graph is rather complete, then the running time will just towards the worst. Close to complete. Okay. That's about the structure, and then at the end, we're going to get two outputs, and I'll get to inside the inner loop a little bit more, okay, before we start tracing something. Upon the completion of the Dijkstra algorithm, there are two things we can make use of, okay? One is about the capital D value for each vertex. And the capital D value here, okay, let's now distinguish between what these two notations really mean. Capital D versus lower d. They have different meaning, okay? So capital D is the weights of shortest path so far. And the little d, right here, will be the true shortest path weights. So we want to make sure at the end of the algorithm, the capital D value, which our algorithm is going to return, will really be correct. So it will be exactly equal to the true value. Okay? I'll get to the distinction a little bit more once we start tracing. Okay? So the little d here is the true weights of the shortest path. All right. Let's dive a little bit more into it. Okay. Let's see what's happening. Okay. Initialization, what we have is we have some priority queue. So for initialization, imagine that we have this priority queue. A little bit similar to breadth first search and depth first search. You have to choose, not really called start vertex. You got to choose something called a source vertex. All the shortest path we're going to compute is going to be relative to this particular source vertex. Okay, so I'll get there a little bit later. So here we have something called a source vertex. And in this case, let's say the vertex is simply S. At the initialization stage, we're going to put everything into the priority queue, including the source vertex. And we're going to set some value, okay? For this particular source vertex, the capital D value will be set to 0. And another value is called ancestor. For now, just understand it's somehow some vertex reference that we have to store. Eventually, we're going to use this ancestor reference to figure out the shortest path. Exactly. Okay, that's something we'll see as well. And this one here will just be nil. Nil is just like a null, right? It's just like a standard notation, nil. Okay. I think maybe when the algorithm was first designed, Dijkstra simply used the word nil. Okay, we're just going to use that convention. Okay. What about every other vertex? For every other vertex, the D value for every other vertex X, it will be plus infinity. And their ancestor will also be set to nil as well. one thing you can see right away. Let's say for the capital D value, with this kind of setup, we set the capital D value for S to be 0. We set everything else, D value, to be plus infinity. What does that guarantee?
If you don't visit any node, that means they're in another tree, so the distance is going to be infinity.
We don't have to worry about like a visiting tree. It's not like a depth first search or breadth first search. Not exactly. It's even simpler than that. All right? So the consequence, yeah, I'll just take, yeah, go ahead.
We assume they are unreachable.
No, nothing about reachability. Even simpler. Remember for priority queue, we choose the one, we choose the entry with the lowest key. And the capital D is used as a key value. Now, if I want to choose one entry from the priority queue, is it guaranteed the first one that's going to be chosen? S. Because 0 is definitely the minimum compared with all the infinity. All right? All right, there's some observation. There's some special setup we have to understand. Okay, so this one guarantee. So D is the key of priority queue. So that means the source vertex X, source vertex S is chosen first. Meaning that we're going to start processing from S. Okay, it's guaranteed. But we're going to see that again once we see the concrete example. All right. All right, so that's about initialization. Nothing else to say, but just remember we're using a priority queue. And I'll cover priority queue after we talk about maybe looping variance and a little bit more about correctness for Dijkstra. And then we get to the priority queue. Okay. Let's talk about this part here. Okay. Basically, that one is saying the following. Let's understand visually what's happening, so it'll be a little bit easier when we try to trace it. So now we talk about individual iteration for the inner loop. When we talk about iteration, and before I even talk about it, let's have an analogy, maybe from 1022 or maybe 1021. Let's say you're given an array. I want to find out the minimum value from the array. What do you usually do? Let's hand wave a little bit. Analogy here might help. Let's say I got this array over here. I want to find out the minimum value. One way to do it, I can say the minimum the result will just be array at index 0, let's say. And then I'll simply run a loop starting from index 1. And then I'll try to run a loop from index 1 all the way to the largest index. Okay, largest index. And let's say right now, I am at the index I. What should I do in this iteration when I'm visiting the element at index I? Guys, it's only 1000 level, right? If you can understand the logic here, you basically understand the core logic for Dijkstra. Yeah, go ahead. Yeah, which two value? You mean the one you have in your variable? Yeah. Yeah, thank you. Exactly. Okay. So here you're basically saying if the current value here, AI, is less than the result so far, that means the result, yes, that means the result should be assigned to AI. It should be updated for the minimum, right? We basically keep finding what can be the minimum, for the whole array. If you find something smaller, that should be updated. Dijkstra algorithm basically follows through this very little insight we have over here. Slightly more complicated when you compare the equality, right? But we'll see, okay? All right, having this intuition here, let's now go back to here, iteration, okay? Let's now imagine this. Somewhere in the middle of the algorithm, what we have is, again, we got priority queue. And then we got vertices still remain in the priority queue. And we choose the U here that has the highest priority, meaning that the minimum value of capital D, right? At this point, let's say the U here, the capital D of U is the minimum. Let's extract that from the priority queue. All right? And then we're going to see if we want to, and then we're going to go over all the adjacent vertices that's reachable from by one edge from U. Okay? Let's visualize this. Think about we got U here, right? Remember we chose U because it got the minimum value for D. U here, and then you got a bunch of adjacent vertices. Let's say one of them is V, let's say. All right, so now here's a critical part. There is some value for U, capital D of U. There is also some value, capital D, for V. Also, it's a weighted graph. We also have the weight right here between U and V. Right? So this is what we got before any update can be done. Since we are calculating the shortest path, every time you're visiting an adjacent vertex, in this case, V, we want to ask about, is this D of V the minimum possible? Can we make it smaller? What should we do? What you do is think about this U here. Okay, let me put it this way. Let me give it more annotation. The D of U here is the weight of shortest path from the source S to U. And similarly, the V here, the D value here is the weights of shortest path from S, the source vertex, to V. And importantly, so far. All right? If this is the shortest path from S to U so far, if I try to traverse from U to V by adding this weight, if somehow that value can be strictly smaller than the current value of D of V, what does that mean? That value should be updated as the shortest weights so far. All right, I'll write it down. Okay? It might seem a little bit abstract, right? I just want to give some, even 10% intuition is enough, right? And then we'll see the concrete example. Okay? And for this part here, let me write it down precisely. Okay, I'll put a star here. Okay, star. We're going to say if this value here, the D of U plus the weight over here between U and V, if that one there is strictly less than the current minimum, that means this value here should be updated because it's something that's even shorter than that. We've got to keep doing this. Okay? Update D of V to this expression. Okay? Let me say this is value V prime. Okay? Just take some notes and get some intuition. Even 10% is good enough. Okay? We got to keep doing this for all the vertices we're going to process. And then eventually, we're going to, every time after visiting all the adjacent vertices of a particular vertex, we're going to remove it from the priority queue. Once we have done that, we're going to keep removing until the priority queue is empty, and then magically, we'll get everything working for shortest path. Okay, we're going to see. Okay? One more thing to say. So here, you can see that. Let me highlight it. Set this value here. All right? You can think about this value here is exactly the V prime I just mentioned. Right? Seems to be an assignment. Seems to be, right? However, the running time is not really constant. The reason is because, remember, it's a priority queue. If you modify the key value of some node in the priority queue, like a heap, it's not really constant time operation. I'll mention that a little bit vaguely, but we're going to go over the details later. All right? So this part here, star, star. changing the key value of an entry in a heap causes up heap bubbling. And this is something we'll review from 2101. It's going to be big O of n. N will be the number of vertices that's actually in the priority queue. All right, that's something we're going to see. But I just want to tell you that this part here, like an update, it's not like a simple primitive assignment that's going to be constant time. Not really. Right, so when we talk about the running time later for the Dijkstra algorithm, that part there is not exactly. Okay. Oh, I do apologize. I said something wrong here. Okay. The running time here, if you do up heap bubbling, is going to be log n, not exactly n. Sorry, not linear. Okay. It's going to be log n. So this part here, I'll make it more precise when we get there. Okay. But for now, just good to mention that. Because up heat bubbling, which will be log n time. Okay. So that's a Dijkstra algorithm. Okay. Yes. Oh yeah, sure. Let's say in Java, you can say maybe the maximum integer. I would say maybe you can just do maximum integer. That'll be okay. Assuming that when we do the addition, it's never going to wrap around. You can just use a maximum integer in Java. Yeah.
But then when we check for the condition, right?
Mm-hmm.
Wouldn't it wrap around since every d of u is set at infinity, correct? At the very start.
Yeah, I would say at this point, let's focus more on the conceptual level for infinity. I think for programming, also it depends on, sometimes you can make some assumption about what's going to be the largest weight for your particular application. Maybe you don't necessarily have to use a maximum integer. Maybe you can say the maximum weight I might have will be 5,000. That might be realistic. In that case, maybe you can make it 5,001, right? Yeah. But that's more like an implementation decision. Let's not bother with that just yet. Yeah. Good. All right, let's now do tracing. Okay. We're gonna, let's do a little bit, and then we can take a short break and then continue after the break. Okay. Oh, actually, you know what? I think what I really meant to do, give me just 5 seconds. This one's supposed to be here, and this one's supposed to be here. All right, that's for today's note. There we go. Okay. There are two examples I prepared for Dijkstra. Let's do the harder one in class. The easy one is actually almost like a no-brainer. Okay, for example, what will be the shortest path? Let's say this will be the source vertex. What will be the weights of the shortest path from x, from W to x? 40. There's only one way to get there, right? And also to go from W to y, there's also one way. So the shortest path, the weights will be 30, and etc. That one's really easy. Right? But I would suggest maybe when you try to do this one on your own, try to follow through how the Dijkstra algorithm is going to process and see how you can get it done. Right? Just by looking at the example visually, just get some intuition. But I'll leave that to you. That's for later. That's for you to look at. Let's look at a more complicated one here. Right? Now it's good enough for you to get the idea about Dijkstra. And then for assignment number 3, I'll give you something more sophisticated to look at. All right, let's now do step by step. Even before we start, I'll suggest the following, okay? Let's now try to write down the little d. Remember the little d? Oh, and also for our example, the source vertex. So we assume that the source vertex will be W. Okay, we assume. The source vertex may be different, right? In which case, the algorithm is going to proceed a little bit differently. For now, we assume the source vertex is going to be W. So that means every shortest path we're going to compute is going to be relative to the starting point of W. Okay? And let's now calculate the little d, right? So the little d I'm talking about, bear with me. I'll show you what I'm referring to. Last time, we spoke about this notation here. about little d is going to be the little d between two vertices. And I'm going to put the source vertex W here as a starting point. And then this part here is going to be every other vertex. What will be the shortest path from the source vertex to every other vertex? That's the spirit for Dijkstra algorithm. All right? Let's now do that. So let's now simply put down. So I got little d, and then W to X. I can even say W to W, that's fine. Little d, W to X, little d, W to Y, little d, W to Z. So this part here is more like a expected value you're supposed to get at the end of the algorithm. That one is not really calculated by Dijkstra. We want to put it there as a reference point. Eventually, the algorithm should really get you exactly little d. Eventually. Okay? What's the weights? The true weights for the shortest path from W to W? 0, right? Just to itself. That one's easy. All right? What will be the true weights from the shortest path from W to X? Is it 40? Is it 35? 20 plus 5 plus 5, 30. All right? So that's the true weights of the shortest path. What about D from W to Y? 30? 25, right? Should be this and this, all right? 25. Finally, how about from W to Z? 20, right? Okay, there's only one way, yeah. Of course, you can go this way here, but that one is actually more expensive, right? It is very important to have these in mind, okay? But I'm gonna make it a little bit smaller. Okay, and then we're going to trace everything. So, right here. Okay, and let me make one more reminder here. So the little d over here is the true weights of shortest path from W to W, and then from W to X, W to Y, and W to Z, etc. Right? Good. And initialization. Okay, we're going to set the capital D value and the ancestor value. Okay, I'm going to draw a table here for us to look at, and then I'm going to annotate the diagram as well. So initialization. We got four vertices. So capital D value and also ancestor value. All right. And then we got 4 vertices. We got W, and we got X, and we got Y, and we got Z. Okay. And capital V value is 0 for the source vertex. Let's remind ourselves. W here is the source vertex. Okay. It's going to be 0, and it's going to be infinity for everything else. Infinity here, and also infinity here. Guys, you want to maybe shut the door at the back? Maybe a little bit better, right? Yeah, let's do it, please. Yeah. Thank you. All right, and ancestor is going to be nil, like a null, in the beginning for every vertex. Nil, nil, nil. You can think about in the beginning, the shortest path is not defined just yet, but they will be defined after we have computed the algorithm. Okay. Given this, let's now also annotate the node as well. I would say in the test, you don't really have to draw this first table. Just for our first tracing, I want to make it more explicit for you. You may just want to annotate the nodes right away, okay? But let's do it. So here we got the D of W is 0. The ancestor of W is nil, okay? And here, the D of X is infinity, and the ancestor of X is nil. So here, the capital D value for Y is infinity. Ancestor of Y is nil. And then the capital D value for Z is infinity, and ancestor of Z is nil. Right? They're going to keep changing, so that's why it's better to annotate these two values for every vertex in the beginning. Okay, we're going to see. Okay. All right. I would suggest I'll try to give you the layout and also the beginning stage, and then we're going to take a short break, and then we'll do the rest after the break. Okay. Let me make this diagram slightly smaller. Okay. I do want to draw priority queue underneath it. Okay, just put it here. And also in the beginning, we're going to put all the vertices into the priority queue. Okay. The order doesn't really matter as long as you put everything into it. Okay. So this will be the priority queue. And just remind you, the queue here, it's a minimum priority queue, right? Minimum key has the highest priority, which will be the capital D value. All right, so that's important for you to note. And we're going to put all the vertices in there. Let's say we put W, X, Y, and Z. And we're going to extract one vertex at a time. That's basically the outer loop. Okay? And then let's also plan out the main tracing table. It's going to be corresponding to not how many iterations we're going to get for the outer loop, which will correspond to how many vertices we have. We got 4 vertices, so there'll be 4 rows in total. Okay? So here, okay, we're going to get, first of all, iteration number. And then for each iteration, we are supposed to extract the vertex with the minimum D, capital D value. Okay? So I'll put minimum D right here. Okay? And then here, I'll make it general about what kind of changes do we have to make. Okay? Overall, you will see 1, 2, and 3, like a 1, 2, 3, 4, 4 rows. But let's not draw them just yet because some iteration might be a little bit easier than others. So let's not just draw them just yet. Okay? All right. Why don't we take a short break, and then after the break, we're going to finish that. All right. All right. Let's now do it. Okay. Let's revisit the algorithm very quickly. Okay. Let's look at that. While the priority queue is not empty, we're going to repeat the following. You're going to find the vertex U that has the capital D value being the minimum. In the very beginning iteration, it's guaranteed to be the source vertex because everything else has plus infinity capital D value. And then there's one condition I want to remind you guys, it's very important. You don't really have to visit every adjacent vertex of U. Because if you only visit V, if V is still in the queue. Right? Notice this little condition here, but I'll show you when we trace the algorithm. Right? You only try to process the adjacent vertex if that vertex is still in the priority queue. If that's not in the priority queue, you don't bother. You can skip, basically. All right? All right, let's now take a look. So iteration number 1, we're going to choose the minimum D value Apparently, this is the minimum. Everything else is plus infinity. All right? So we're going to choose it. So let's say we choose W with the minimum capital D value. And then let's now write down the information. Iteration number 1. Iteration number 1. The minimum D value, the W, D of W. We're going to choose W because D of W is 0. Okay, so we choose W first. And then this part here, we have to go with the inner loop, which is over here. We have to look at every adjacent vertex to the one that's been chosen, right? So now if you look at that, W, what adjacent vertices do we have? X, Y, and Z. Which one of them is still in the priority queue? Every one of them, because X, Y, and Z are still in the priority queue, right? Good. So what we do is, let's now write down. So adjacent vertices X, Y, and Z, they are still in the queue. We're going to look at every one of them. And let's now look at them very carefully. But the same process is going to be repeated, right? Remember that minimum calculation from the array, right? That we're going to set before the break. Let's now look at this one here. We want to see whether or not we should update the value for the capital D of X. Currently, we are saying that the weight of the shortest path to go to X when there is no ancestor is plus infinity. However, we know that the shortest path, the weight of the shortest path to go from W to W is actually 0. If we actually go from W and then go with this edge with weight 40, what will be the total weights? Will be 0 plus 40. And then I can update this one to be 40 and now have a better root, which means the ancestor changed that from nil to W. All right. For this very first one, let's write it down. Okay. Let me just write it down here. Okay. Just for the first one. So when we have, let's say W, let's be very careful about the first one. Okay. D of W is 0. And A of W is nil. And then we talk about X only. Okay? X, for the initialization, we actually got the D of X is infinity, and the ancestor of X is nil. Okay? Let's understand what's really happening right now. Okay? First of all, this part here, we're saying that when the ancestor is nil, which means undefined, the weight of the shortest path from source vertex W to X is infinity. That's how we interpret that. All right? And then this one here is similar. When the ancestor is nil, the weight of the shortest path from W to W is 0, right? But this is okay because W itself is already the source vertex starting point for the shortest path. Its ancestor, we don't care. It's okay to be nil just for this case, right? And then if you recall, this one here is 40. Okay? What we're going to do is we're going to change this one here to be 0 plus 40. 0 here and 40 over here. So that means rather than having neo ancestor, why don't we change the ancestor to be W? That means if you go with the shortest path as follows, W and then X. This is a shorter path than what it is right now. So go with that. And then you will change over here to W. Okay? The way to interpret this by going W and then X. We have a smaller weight, 40. Okay? The similar argument is going to continue. All right? Okay, having this in mind. Okay, let's now repeat this process many times. Okay? So let's now be a little bit more mechanical. So we got 0 here and plus 40. So 0 plus 40, you can see that it's currently less than the infinity. That means we can now update the d of x to be 40. And at the same time, the ancestor of x can be updated to w. Okay? So this will now be 40, and this will be w. Any question, please? We're going to repeat this many times. If you don't really get this one, it's now time to clarify. Otherwise, I'll just continue. All right, let's continue. So the first adjacent vertex is done. Okay, do a second one, right here. And this one here, we're going to check to see 0 plus 30, 30. Is this strictly smaller than infinity? Yes. Update it. And then update the ancestor to be w. Okay? Similar. So 0, 0 plus 30, right? Less than infinity. That means the d of y, it will be should be updated to 30. And the ancestor of y should be updated to w. Okay? So this part here should be 30, and this part here should be w. All right, one more. And then I'm going to make some observation together with you. The final adjacent vertex will be right here. All right, similar logic. Is 0 plus 20 smaller than infinity? Indeed. Update it. So 0 plus 20 strictly less than infinity. So that means the capital D of Z should be 20. At the same time, update the ancestor for Z to be W. Okay? This one should be W, and the capital D value should be 20. So you can see all the adjacent vertices for W have been processed. What should we do? That means W here is completely handled. Remove it from the priority queue. Remove W from the priority queue. Okay, the first one to be removed. As far as the algorithm is concerned, that's the very first iteration. All right. Let's now make some observation. Okay. First of all, as soon as a vertex is removed from the priority queue, as soon as W is actually removed from Q, there is a property which we're going to try to prove, at least to understand a little bit better later. Okay? As soon as this is removed, we say that this capital D value here is finalized. It's guaranteed mathematically. The capital D value here should be exactly equal to the lower D value. Okay? Already done. this tells us the capital D of W will be guaranteed to be equal to the little d value. And we say that this result is final. At the same time, let's look at the capital D value right now for all the other vertices. Some of them may be already equal to D, but as far as the algorithm is concerned, they are not final yet because they are still in the priority queue. But let's look at them one by one. Capital D for X, this value here, 30 and 40. We're not there yet, but that's okay because X is still in the priority queue. We'll get there. We're going to update it at some point later. All right? So this one here is not exactly equal to the lower d of W26. That's okay. We're going to handle that later. And if you look at this one here, capital D of Y, D of W to Y, 25 and 30, also not equal to, also fine. We're going to handle Y a little bit later. Not equal to D of W to Y. This one here, the capital D of Z, D, W to Z, 20 and 20. They are equal to each other. That's okay. That simply means we already find the minimum value in the earlier iteration. That's okay. But it's not considered final just yet. Okay? Is exactly equal to the lower d of W to Z. And let me say this one here more specifically. Okay? This one here exactly equal to, right? But it's not considered as final just yet. Because the vertex Z is still in the queue. All right? Very important concept. Okay? All right, so let's now do the second iteration for the outer loop. And I ought to make this a little bit smaller. Otherwise, I'm going to run out of space. Okay, a little bit smaller. Okay. So now for the second iteration. Question, which vertex should we pick? Should we pick X because it goes right after W? What should we pick? Remember, it's a priority queue. Diego? Z. Why should we pick Z?
Because it has a lower key.
It has a minimum key. Minimum, yeah, that's important. All right, very good. So now you can see that as of now, we got for all those vertices in the queue, X, Y, and Z, we got 40, 30, and 20. Pick the minimum, right? Good. Okay, pick the minimum. All right, for that one there, I would say iteration number 2. We're going to pick Z. And then because D of Z is 20. Okay. And then I'm going to use orange. Okay, that's the one we pick. Let's preview a little bit. How many incident edges do we have for Z? How many? Are you sure it's 1? How many? 1, I agree. 2, right? However, we only need to consider this one here. How come? Yeah, because the W here has already been removed from the priority queue, so we don't need to worry, right? Not exactly pop, right? That's not the right word, but I know what you mean. Yeah, good. All right. All right, so here, let me write it down. So Z here has 2 adjacent vertices. We got W and we got Y. But W has already been removed or extracted from the priority queue. It's deleted, so we don't need to worry. Okay, I'll write it down. So for that one there, so W is not in the queue. Not considered. So we should only consider the incident edge leading to y. I'll pause here. Okay, anybody can suggest what should I do to process this particular incident edge? I'll give you guys a little bit hand waving to give you some hints. I'm now currently in vertex Z. The value here, 20, tells me that that's the weight of the shortest path to go from W to Z, where the ancestor is simply just W. Now, I want to know, if I follow this edge with the cost 5, is it going to result in some cheaper cost or strictly smaller cost that can replace the current capital D value for y, which is 30? That's my question. All right? Should I update or should I not update? Should I? Yes. Yeah, okay. Because you can see that 20 here plus 5, strictly less than 30. Okay, updates. I'm pretty sure you're still wondering about how exactly should I see how the ancestor is going to help me with the final shortest path. You will see. I just need a separate page for that. But for now, just see how you can update it. Okay. All right, for this one here, we're going to say the 20 plus 5 strictly smaller than 30. Okay, so that means we should read the updates. The capital D value for y should be now 25. Right? And then at the same time, the ancestor for y should be the current vertex that we are talking about. Should be Z. All right? After this, we basically have handled all the incident edges for Z. So Z can now be removed from the queue. So we're going to remove Z from the queue. And what that means is, as soon as I remove Z from the queue, so this will be number 2. The capital D value for Z, which is 20, is guaranteed to be the weight of the shortest path from the source vertex W to there. Guaranteed, okay? Which is 20, okay? So that means over here, the capital D of Z will be equal to the little d of from W to Z, which you can see is right here, right? It's 20. So that'll be final. Okay, let's see one more observation, right? You can see that before, the d of y used to be 30, but now it has been better. It's now 25, right? And 25 is indeed the true value. However, we don't really say d of y is final just yet, because y is still in the priority queue. Theoretically, there's maybe another path that can make it even cheaper, but we just don't know yet. Okay? So that's why we don't say it's final. Okay? I'm going to write it down. Okay? So this one here, think about this 25 here is equal to the little d from the source vertex W to y. Equal to, that's good. However, we don't say it's final because y is still in the queue. Not final just yet. Because y is still in the queue. Okay, we're getting a little bit closer. All right. If you really have been following so far, you pretty much get the essence for Dijkstra algorithm, right? It's a very nice, very nicely devised algorithm. You just got to follow that little logic. But we're going to see how you can prove it a little bit later. Okay. All right. We got 2 more iterations to go. All right. Any suggestion for iteration number 3? Which vertex should we pick? Why? Because you got a minimum capital D value, right? Thank you. All right. Again, for those of you who are wondering, you can see here we got 40 and we got 30. This one apparently is a minimum. Pick that one, okay? So number 3, we're gonna pick Y. And then the D of Y is 25, okay? Right here, okay? And then for Y here, you can see we got 1 and 2 and 3. Incident edges, we got 3. However, we don't need to worry about these 2 because W and Z are not in the priority queue anymore. We can skip them. So you only have to worry about this edge right here, leading to some vertex that's still in the priority queue. All right. So that one there, we're going to see W is not in the queue. And also Z is also not in the queue. So they are not considered. All right, so what we should do is, okay, let me just pick Y. The only one we have to worry about is this edge, right? What does that mean? That means you have to consider D of Y is now 30. 30 plus 5. Is it strictly smaller than the current capital D value for X? Yes, updated. Awesome, good, good. Very nice. Oh, actually, you know what, guys? I think there's some terrible thing. I think the table is exactly correct, but I forgot to update the diagram, I think. Right, let me see, okay? So let me double check. Okay, so I think after the first iteration, I think these are okay. So now after this one here, I should really update D of Y to be 25, right? That one also tells you when you actually do in the test or exam, make sure you update both the table and the diagram, right? Don't be like me, okay? So 25 here should be updated, right? So what we are really asking is the capital D value for Y, 25 plus 5. Is it strictly less than 40? Yes, right? Just got to make sure you update the right value, okay? Please. So I'm going to write here. So 25 plus 5, strictly smaller than 40. That means we have to update the D of X. Should be updated to 30. Right? Updated. And then at the same time, you should also update the ancestor of X to be Y. And of course, from the previous iteration, you can see A ancestor of Y should be updated to Z. Again, I didn't do it. Ancestor of Y should be Z. Right? These information are very important. So when you practice, make sure you do in sync. Okay? Okay, that's good. Yeah, question. Okay, thinking this way. Whenever, let's say here, in the beginning, we got neo as the ancestor for every vertex, right? Let's say for here. Right here, because the vertex that's being picked in the current iteration is W. If somehow through W, you can find a cheaper path to update the capital D, and then W should be the new ancestor. On the other, let's say for this one here, because Z is actually picked as the current vertex. If somehow through Z, you can actually find a cheaper, shortest path, you should really update Z as a new ancestor. So that's why here you can see we got Z over here. Right? You can think about in the actual shortest path we're going to produce, the ancestor will be the one just appear before you. Yeah, we'll see exactly, yeah. All right, guys, final iteration. And of course, after this, we're going to remove y from the priority queue. And that one there will be number 3. So that means the d of y will be exactly equal to little d of w to y. And that's considered as final. Okay? We only got one vertex in the priority queue, so we still got to do one more iteration. But that one seemed to be quite trivial. So we only got one. And what's the minimum? Only this one here, right, with 30. That's the one to pick for x. And that one there. Okay. Let me just say I'm going to continue. Okay. So iteration number 4. Okay. We're going to pick x. So d of x is actually 30, right? That's the minimum. So we pick it. However, do we need to process any of the adjacent vertices? Right? We don't need to, because you got 1 and 2 adjacent vertices, but none of them is still in the priority queue. Nothing to do. Awesome. Okay? All right, so nothing to do, because the w and also y, the adjacent vertices, they are not in the queue. And after this, we're going to remove x from the queue. So that means the capital D of x will be equal to the little d of w to x. Okay? That's final. This one here will be final. And then we also got to remove it, right? Yeah, slightly messy. I do apologize, but you see the point, right? So final iteration here, x, basically we pick it, but there's nothing to do because none of the adjacent vertices is still in the queue. And one final thing I would like to do, hopefully that's enough time, is to see how we can interpret the result. Okay, x over here, and then we're going to remove x here. So now if you double check the capital D value, this one here equal to this. For z here, 20 equal to this, and etc. You can check every one of them, right? The capital D eventually will get to the lower d, the true weights of the shortest path. But let's now worry about ancestor. How do you actually understand it? Okay. Let's now try to make things summarize about a result. Right? Let's focus on just the ancestor. It turns out the ancestor. Oh, did I update the ancestor though? I think I did. Yes. Okay. Good. So what I will do is let's not only put the ancestor value. Ancestor of W remained to be nil. It was never updated. The ancestor of x was updated to y. The ancestor value for y was updated to z. The ancestor value for z was updated to w. Right? That's what we have. Let's see how we can interpret the result. Okay? Let's use a table. Think about each vertex is the destination with respect to the starting point, which will be the source vertex. So destination will be x, y, and z. We're going to look at each one of them. And you can make a short notes over here. Destination is really with respect to the source vertex. As starting point. All right, so now we're just going to follow through the ancestor. Okay? We're going to get something called ancestor path. However, for this ancestor path here, don't really confuse with when we talk about binary tree or tree, like an ancestor path. It's not exactly that. Okay, ancestor path. Let's go talk about what's the ancestor path for X. Start with X itself. And then gradually look it up. Ancestor for X is Y. What is the ancestor for Y? Z. What is the ancestor for Z? W. What is the ancestor for W? Neo. But you can think about neo, it's just ignored. Accordingly, we still got our destination, X, Y, and Z. And we talk about the shortest path, which will be from the source vertex W. The shortest path will just be the reverse of the ancestor path. It's going to be starting from W, making sense because it's a starting like a source vertex. W, and then Z, and then Y, and then X. That tells you, given this particular source vertex W, if I want to reach to X, what will be the shortest path? You go to Z, go to Y, go to X. That will be the shortest path with the minimum weights. That's how you interpret that. And the amazing part about Dijkstra algorithm is once you complete the algorithm, the ancestor path can be computed basically for every vertex with respect to the source vertex. So when you want to calculate for the source vertex, so whenever you want to start the Dijkstra algorithm, picking the source vertex is so important, right? So let's say if I want to find the shortest path between X and Y, you pick one of them as the source vertex. You got to make sure you do that, right? Okay, let's complete this. And then I think we should be good for today. Okay. And then we got Y. What will be the ancestor path for Y? So we start from Y, right here. So Y first. Ancestor for Y will be Z. And ancestor Z will be W. And then ancestor for W will be neo. Right? And accordingly, shortest path will be W, Z, and Y. Okay. I'll make one more annotation for you. Okay. Think about the Y here is the ancestor of X. The Z here is the ancestor of Y. And the W here is the ancestor of Z. Okay? I think that will help. One more. And I can also put like that. Okay? Final one. Let's say, well, what about ancestor path for Z? Z here, ancestor for Z is W. Ancestor for W is neo. W. All right? Oh, I got to start from Z for sure. I forgot, right? Got to start from itself, right? All right, so it's going to be W and Z. Shortest path. Right, so this will be the only Dijkstra algorithm we're going to do in class. We wouldn't do another one in the tutorial. I'll give you another one in the assignments. So I think tomorrow we're going to adjust a little bit, right? Since I wish I could cover a bit about looping variants. Maybe tomorrow in the tutorial, I'm going to give you some mini lecture, maybe in the first half about looping variant and also some syntax, and then we'll do some half of the exercises. We'll continue with the exercise also on Monday to complete it, right? All right, thank you, and then I'll see you tomorrow.